So I'm going to tell you about some of our recent work on tubular robot continuum structures for surgery and kind of some other research highlights along the way. So these are the people that contributed to the work you'll see in my slides today. This is all the grad students and postdocs that have come through my lab in the last 10 years or so. So the current crop of students and postdocs is on the bottom row, but I'm grateful to all these people, and there's a lot of work that went into building everything that we've been doing, and so I'll try to call them out as their work shows up. I also want to just recognize the excellent team of people I've been working with at EndoTheia. This is a company we started back in 2018. Bob Webster, Josh Gafford, Scott Webster, Duke Carroll, and I. And it's grown. So we have a great technical team of engineers. We also have some great partners at Nisha Medical that are helping us get things really off the ground, and that's very exciting. It's just really exciting to be a part of such a great team. And so I may tell you more about that as we have time. So we're in Knoxville, Tennessee, in the Great Smoky Mountains. Sometimes we go on hikes in that park. It's only about 45 minutes away from our lab. So it's a great area of natural beauty, as you also have here in North Carolina. And next week, I'll just put in a plug. I think some of you are probably going to come down for the International Symposium on Medical Robotics in 2026. We're hosting this in downtown Knoxville, which is very pretty. And so I look forward to seeing some of you there and maybe in the future. So I know some of you in the audience are very familiar with this idea of a continuum robot, but we'll start here with what a continuum robot is. This is probably the main theme that we've worked on in my lab over the past decade. We've done a lot of other things as well, but everything kind of is around this idea of a continuum structure that becomes a robot. So you can think about the serial robot structure. It has a number of links and joints. And as you increase the number of links and joints, you get what we would call a hyper-redundant robot. And then in the limit, as those links and joints go to infinity, you might even say there's no joints, even though, or maybe there's infinitely many joints. I'm not sure which we should say. But it becomes a continuously bending, a continuously flexible structure that can change its shape at any point. And so if you think about the categories involved here, a continuum robot is an under-actuated structure. It's kinematically hyper-redundant. Not all of its degrees of freedom are directly actuatable. So it's in that big category of robots. And then soft robots, which is a much more well-known term now, is just robots that are made of soft material. And those are by definition part of the continuum robot landscape. But you can have also continuum robots that are made of hard materials, like super elastic metals, like nitinol. And so this is kind of my Venn diagram for how to visualize these things. And a lot of the time, the people that have been studying these for a long time have really been inspired by biological structures like snakes, vertebrate structures like long flamingo necks, as well as muscular hydrostats, which don't have any bones in them, but things like your tongue or an elephant's trunk or an octopus tentacle. So technically a vertebrate structure is actually multiple links, hyper-redundant thing, but we often approximate them as continuum because they have so many degrees of freedom. It was interesting so as we present in this area, we often call back to history and try to imagine what the first continuum robot is, and you can look back in the literature and see that in 1965 there was a group at Stanford University that made this thing called the ORM, which is I think a Nordic word for snake, and it had 28 inflatable pneumatic bellows actuators. So technically this is a hyper-redundant quasi-continuum robot, but it's what we have been calling the first continuum robot of the modern robotics era. So it really goes all the way back to the beginning of robotics. But recently, I discovered that there is an even older Continuum robot that I would like to propose as the real first Continuum robot. In 1733, this is an automaton created by English watchmakers John Joseph Merlin and James Cox. It is driven by 3 spring-driven clockwork motors. It has 113 degrees of freedom in its neck. In these neck rings, there's the mechanism that's inside those neck rings is a chain-driven structure. And it has a bunch of spinning glass rods that simulate the waves of water. It goes down and catches a fish. This thing was on display at the 1867, maybe it was World's Fair, and Mark Twain wrote about it in his 1869 work, The Innocents Abroad, and described having seen it at that exhibition. So Continuum robots have actually been around a long time, maybe even before, the the robotics era. And I think this is just incredible that this long ago, there was this excellent engineering. Was that? Yes, it's at the Bowes Museum at a castle in England. And this is its main thing, that you can go see it. It still works. It's been restored, and it actually does this. It's got sound effects and chimes and stuff like this. Yeah, so James Cox is an amazing inventor. You should look up more of his work on automatons. But I just had to put this in here as having recently come across it and been very inspired by it. But in the modern robotics research landscape, there's been a lot of different exploration of this idea. There's a lot of different ways to make Continuum robots. They can be pneumatically actuated. They can be hydraulically actuated. They can be actuated through shape memory alloys. They can be actuated by piezoelectrics. They can be driven by tendons that you pull. They can be driven by rods that you push and pull. And so usually there's a structure that gives the thing some underlying flexibility and maybe some elasticity to bring it back to restore its shape. And then there's some element that tries to push, pull, elongate, shrink different parts of the structure to make it bend in various ways. Okay, so I'm going to talk about in this talk some themes of benefits and challenges that we are trying to create and also mitigate in this field. So these robots can potentially navigate in confined environments inside, winding passageways. They're able to adapt to constraints, external constraints, without exerting large forces. So that's important for interaction with sensitive things like biological tissue. One big benefit I see is that a lot of times these robots can be designed with non-collocated actuation. That means that the motors that are driving things are located not on the body of the robot itself, but off the structure, perhaps in an actuator pack remotely. And then for that reason also, it's possible to miniaturize a lot of times these structures to the point where they're really useful in areas like surgery. And their inherent flexibility also gives them the ability to act as sensors themselves. If we can look at their deflection and sense the forces that must be on them using appropriate models. Challenges is, the same flexibility that gives all these potential advantages also limits the force that can be applied by these devices. And often they're limited in their workspace and dexterity because it involves the bending of material that has strain limits. The workspace can also be limited by the force limit because, it's great if you can bend around in a large space, but if you need to apply force, the space you can really work in is probably lower. And then a big one that we've studied a lot in my lab is how we understand the complexity of these structures and how we model them accurately and then control them. And that's largely driven by the underactuated nature of them. So we can talk about modeling. You guys are probably in robotics courses that have talked about rigid link kinematic models for robots. The analog to that for Continuum robots is a thing called constant curvature arcs. in which you have a link-to-link transformation that propagates along a circular arc. That's been studied for a long time. And then if you want to go, fully describe the under-actuated nature of these things and the fact that they can really bend anywhere, you need some kind of continuous model, which talks about not just a set of finite reference frames, but an infinite, a function, a reference frame that's a function of arc length. So that's the kind of model we typically try to work with and develop for our devices. I'll show these. Here's just some consequences of the under-actuation. Here you can see, like, this robot only has, on the left, we only have two tendons actuating it. And so normally it would bend, in steady state, it would bend to just a circular arc. But because of the dynamics of the way it's being actuated, it's exciting this mode that is not the constant curvature mode. So even though the robot's designed for constant curvature, in a dynamic sense, it doesn't, right? And there's this other mode, and there's even higher order modes that you can see. And so here, if you're just trying to do a step response to get the robot to go to a desired curvature, it takes a while for the transient vibrations to settle down. It's difficult to control all of that through the single actuator. So this is where we kind of get into some necessity to model things. This is my diagram of this is most of the math that's going to be in the presentation is just this. Kind of pared it down to the more exciting non-mathy slides today. But basically, we're dealing with the kinematics of a homogeneous reference frame that propagates along a reference line. So most of the time, we're defining the backbone line of a robot. And there are material constitutive laws that relate stress to strain. There are mappings between strain at an element in the cross section to what we would call Courserac variables U and V, which are curvature and extension and shear. And then to relate all this together, you need some notion of equilibrium, of force and moment balance, which can be written in statics or in a dynamic way. So we've done a lot of publishing on this type of modeling and came up with some efficient numerical techniques to simulate the hyperbolic partial differential equations of Courserac rods. So there's a number of papers there, and this is kind of the end result. We can do this kind of thing in real time and simulate these large degree of freedom systems efficiently. One question is, how would you use such a model for control? Well, I've got a slide on that later, but so we can do different robot structures. We can do tendon-driven, rod-driven, pneumatic-driven, all by using that underlying rod model with appropriate actuation terms. Further in this realm, this is very recent work that we're doing in the context of an ARPA-H project on surgical robot automation. This is the work of my student Sam Tobin, who's been developing a simulator for soft tissue dynamics coupled with the dynamics of a Continuum robot. So you can see these arms are actually concentric tube robots that are supposed to be modeling the concentric tube robot arms of the Virtuoso surgical robot platform. And what we're doing here on the right, you can see some adaptive mesh refinement. So as the tool approaches the mesh refines, and then the tool has some cutting dynamics with the mesh. And once the tool has cut the mesh along a refined mesh domain, that refinement stays there. But if the tool moves away from a region that's not cut, it can coarsen back. So this helps us handle the computational burden. We can leave some parts of the mesh coarse. We can adaptively refine places that we're about to cut. So I'm very excited about this work. This is all real-time simulation for many thousands of nodes and elements here. We're using this model in the context of a perception pipeline where we're fusing it to data that can be gathered from an endoscope. And we're also using this model to train learned models for automating surgical subtasks. So I won't go too far into that, but it's on the theme of modeling, and I just love the smiley face that Sam is drawing here. Yeah, so another aspect we could talk about is the intrinsic sensing potential benefit. So we've done some work that takes those basic rod models and does an inverse problem. So if you can see the shape of the deformed rod, can you tell where and how large the forces are on that structure? And it's hard to think about how to do that. I mean, it's hard to imagine doing this as a human. I don't know if I would be able to tell exactly where this force was just by looking at the curve from the vision. But the rod model can do this, and we can solve for this force distribution by looking at the robot. We're doing this in more of a practical situation, again, in the context of our project on surgical automation. We're looking at surgical palpation. So we have a concentric tube robot here that's pushing on tissue, and it's actually measuring the stiffness of the tissue by looking at the deflection that the tip is doing. We have we're going to push into the tissue, and then the difference between where we would have expected the robot tip to end up and where it actually ended up indicates what the force on the robot is. And then the displacement that we achieve there tells us something about the stiffness of the tissue at that point. We take a bunch of stiffness measurements, maybe 10 by 10 grid here, 100 points, and we can make a stiffness map. So we fit a surface to those points, and we can get a picture of, oh, there's a high stiffness region right here in the middle. There must be something hard underneath where I was pushing at that spot. So this is trying to localize a subsurface simulated tumor that's about 5 millimeters below the surface. And we get okay localization here. It's a couple of millimeters of error. I think a lot of that may be just due to registration and model inaccuracy. But whereas it's an ongoing process where we're looking at different ways to do this with, in this case, magnetic tracking. We're also looking at ways to do it with the endoscope vision. I mentioned model-based control and how it's hard to do control in the context of those highly underactuated dynamics. So we've done a paper on this in the last few years, a couple of papers on this, where we use a physically motivated observer structure to take measurements of single points on the robot, maybe at the tip and at the midpoint, and reconstruct the entire robot state from that. And that's what you need if you're going to have feedback of the full shape, that you would need to do a closed loop feedback linearization type of controller. So in this work, we're showing that the typical feedback linearization type control approaches can actually work on continuum robot models that are highly underactuated, even though it is maybe commonly assumed to be difficult to do that. Okay, so I'm going to talk a little bit more about force limits. And this will have application to some of the tubular robots that I'll talk about for the main part of the talk. This is a well-known phenomenon with just a single segment that you might actuate with tendons, is that, when you actuate them, you get this constant curvature segment. Then if you hold them still, if you say it's okay, the robot is straight, and then you hold the actuation lines at a constant displacement, if you then put a force on the end of the robot, the structure will bend in this S-curve shape because the actuation lines are not constraining it from doing that. And so this is the unactuated mode of the robot, and when in response to an external force, this is the mode shape that it takes. And so this introduces, some limit on the force that can be resisted here. If we take this same robot and simply make the backbone the inextensible backbone diagonal across the robot. This forms basically a truss structure between the actuation lines and the backbone. Triangles are strong, right? I mean, so in this way, when this force transverse load is applied, the underactuated mode is eliminated by the structure, and you get zero deflection in the idealized case here. So this is a way to, but it doesn't take really any more actuation force to do the constant curvature actuation in this robot than it would normally. So you're getting same amount of actuator effort involved in moving the robot around, but the ability to reject external loads much, much better. So we made a robot that does this. So you can see here's the underactuated mode of a typical Continuum robot. We put 900 grams of weight on it, and it just sags to the floor. Even under its own self-weight, it's sagging quite a bit. And then in contrast, our diagonal backbone robot, there's just zero. I mean, we couldn't even measure the amount that it went down because it went down so little. And it's same if you've got the backbone going against the load or towards the load, up or down in this case. You do have to have, this is for a push-pull rod driven thing, because in some of these loading cases, some of the actuation rods are in compression instead of tension. So it wouldn't work completely the same way for a tendon-driven robot where the tendons can't hold compression. But we can load this robot up. You can see this is a video. There we go. So the top video is the robot without any weight on it, and the bottom video is the robot with 200 grams of weight. We've got two of these segments concatenated together. And you can see not only is it not sagging, it's also it's making sharp turns and abrupt corners without doing any underactuated vibrations, even though it has a large mass at the end. And the difference between the two trajectories in the loaded and unloaded state is very, very small. Just play that again. So this is a theme that we've been looking at for a while now. We have a couple of papers on this where this is actually coming out. We'll present this at ICRA next month. So you can look forward to the full presentation of that, but I'm stealing Ethan's thunder here a bit. Ethan Eisenhower is an undergrad student who kind of spearheaded this work. But we can take the lessons learned from this and apply it to other continuum robot structures as well. Tendon-driven with converging tendon routings, and then later tubular robots with similar structures. Okay, so for the majority of this talk now, I want to talk about this one particular structure that we've been working on called a concentric push-pull robot. And the real motivation for this structure is the challenge of internal space limits. We want to save as much space as possible inside a tubular lumen so we can run anything we want, right? Cameras, therapy lines, laser fibers, gripper actuation cables, things like that, inside of a hollow lumen. And we also want to miniaturize this as small as we can get it, because we want to put it in very, very small places in the human body to help surgeons have better capabilities. And we're also kind of really looking at the non-collocated actuation problem, because we're going to do these things through long endoscopes, and we need to be able to transmit the actuation forces across long, flexible pathways. So the idea is you take two tubes, and let me just pause this really quick. So these are thin-walled tubes, perhaps metal, perhaps plastic, and what we do is laser cut a series of slits into them, and we do it on one side of one tube and on the other side of another tube that is slightly bigger. And we put these tubes together concentrically and we weld their tips together. And then when you push and pull the bases of these tubes, the patterned section, the asymmetrically patterned section, actively bends. So this is similar to a lot of other continuum robot structures that have been developed. It's similar to tendon-driven robots. It's similar to push-pull rod-driven robots. And the key thing is that we're trying to simplify that sort of structure down to its basic elements. Usually in these robots there is some kind of backbone structure that holds, channels for tendons or something like that, that constrains things together, and then there's driving elements. And so what we're doing here is we're just combining. We're saying, well, can we just make the driving elements also be the containing structure? Can the two driving elements constrain one another? And that's what we're doing with these tubes. So it works because of the offset in the stiffness center that occurs when you asymmetrically cut the tubes. So one tube stiffness center, or neutral axis if you like, is shifted to the right, one is shifted to the left. Those locations now function as the push-pull rods, even though they're part of a larger tube. So we've been thinking about these for, I think the first time I thought about it was in my career proposal in 2014, 2015, and then our first paper came out about it in 2017, in which we were 3D printing these and trying to understand the geometry and how they would work, and developing the first constant curvature models of them. And then we quickly kind of realized that, there's a lot of different cut patterns we could do. We could have these large rectangular notches, like I've shown, or we could do something more monolithic, in which we cut very small slots, but cut a lot of them, and we let the slots interleave. And what this creates is a continuous pathway of material. If you can see my mouse over here. So you could imagine like winding around this way. We call this a serpentine beam design pattern. It helps with the resulting torsional rigidity of the device, because it's connecting the material around the front end as well as the back. So it also, it just presents more of a smoothly actuating structure. You can see in this video, some of the slits passing other slits kind of in the gaps. All that happens really smoothly. There's not really any snagging. These tubes are very cleanly machined. And if you think about it, one tube's smooth backbone that's uncut is always rubbing against the other tube's cut side. And so the forces that are involved between the tubes are never like cut on cut, really. So it does go cleanly. There's relatively little friction involved if you have good polished tubes. And we can transition from an asymmetric pattern of a tip section that's designed to actively bend to a symmetrically patterned transmission section, which is designed to passively bend, but also transmit the axial forces necessary to actuate the tip. And when we do that, we can put the passive bending section inside some other structure, that like a long flexible endoscope to guide it to a location, or inside another concentric push-pull segment. So we can put this distal segment inside a proximal tube pair that's also designed to do bending. Here's the passive symmetrically cut section. This is a design that's common in catheter construction. We call it a brickwork design, where you have these kind of just overlapping symmetric cuts stacked up like bricks. Here's a demonstration that, in fact, there is no crosstalk across sections. So if I just push and pull, even though this section is flexible on the left, it doesn't try to bend when I push-pull actuate the tip. And then we can bend that section into a flexible path, and we can still actuate the tip just fine. So this kind of eliminates maybe the typical crosstalk problem that might occur in a tendon-driven system. So we got fancy and tried to make really elaborate versions of this that would do different things. Here's the kind of two-tube manipulator, or two-pair manipulator, just doing some motions. This pair on the right is not perfectly matched in diameter. It's just something we put together quickly. We can also do this with more than 2 tubes per bending segment, and if you do that, you can get active control of bending in multiple planes, and then you can twist all the tubes together to reorient the tip. And finally, we can make these really small because hypotubes can be manufactured at very small scales, even sub-millimeter diameters. And then the capability exists in industry to laser cut these tubes with very fine precision. So this is with femtosecond laser cutting on nitinol. And this is I think the outer manipulator on here is about 3 millimeters in diameter, and these are about 1.5 at the tip. So video credit here again to Josh Gafford at EndoTheia to make that. All right, so we'll talk a little bit more about complexity and accuracy of modeling and control for these robots. I want to be wise on time, so let me know when I'm running close to the end. 40 minutes was the budget or so? Okay. All right, so you can imagine this just generates a lot of interesting questions about how you might design variable curvature shapes into these. You can encode a desired deformed shape by patterning the notches in a certain way. So we have a paper on that. And then we've been spending a lot of time trying to understand the mechanics of this, how we should really model it. And we have one paper on this that's basically an energy minimization model in which we first take the design parameters of the slot patterns. We characterize the basic bulk bending rigidities and torsional rigidities and neutral axis offsets of that design pattern. And then we put these into our energy method model with actuation, external loads, and outcomes of the shape. So with that approach, we find pretty good prediction accuracy in various cases. And we can do the converging actuation design, again, to increase the force capacity at the end of these things. This is just lifting a very large weight according to the robot size. And this is made possible by the converging tapered stiffness centers. I'll just quickly run through. The force capacity is also influenced by the properties of the long transmission. We're trying to put these through medical endoscopes. So we want the transmission to have a high axial stiffness, a low torsional stiffness, and a low bending stiffness. So we've done some work on optimizing the pattern that goes in between the tip segment and the actuators. And we can actually decouple the axial from the bending stiffness, which is kind of a new result in that area. I'll just run past this. So our application here, the main thing we're working on right now is an NIH project in which we're doing endoscopic submucosal dissection for cancer in the colon. So this is kind of what that procedure looks like. You insert a needle, you lift up the lesion by inserting a saline solution. You then have an electrocautery that cuts circumferentially around the lesion, and then you lift it up and take it out. It's a difficult procedure to do for large lesions, and so we're trying to make it easier for doctors to do this by giving them dexterity at the end of their endoscope. So we built this system. You can see here there's an actuator pack, drives the tubes over a long transmission. We'll see that in a second. Long transmission. This is why we need that transmission to have the right stiffness properties to go through the scope and transmit those push-pull forces to the tip. And we can set this up in either a single pair configuration or a nested pair configuration. Here's some videos of the first nested pair design that we've done, and we're currently doing experimental characterization of this in ex vivo tissues, leading up to some porcine trials towards the end of this year. Here is our control system. We have the input devices for the operator that encode the 6 DOF desired motion, and we're using a damped least squares Jacobian servoing algorithm to get the motor commands. Here's a video doing electrocautery on a chicken breast with the manipulators. And finally, here's some trial with ex vivo porcine colon, in which we're actually doing the ESD procedure. It's a little hard to see because there's smoke on the endoscope viewpoint, but we are cutting through only the mucosal layer, and we are successfully removing a simulated lesion inside this porcine colon that we set up. So we can, it's 12:40. That is technically the last slide. I do have some information if you want to talk about the EndoTheia endeavor. We can go through that some, but maybe we can just stop here and take questions first. And what do you think? Okay.
We can also do 5 more minutes and take some questions and then go through them.
We can do 5 more minutes. That's fine. Yeah, so like I said, EndoTheia, we started in 2018 and moved buildings a couple of times. We were originally incubated in the VISE space at Vanderbilt, the Vanderbilt Institute for Surgery and Engineering. And now we're moving into the NISHA Center of Excellence tomorrow. NISHA is a strategic partner of ours, and they've set up a new engineering center in Nashville. And so we're excited to be moving into that with them. Here's the team again. One of our first products that we're looking at, and we've done several human trials on now, is removing lower pole kidney stones through a ureteroscope. And so these are challenging stones to remove because they're in a difficult to reach location, and oftentimes even if you can navigate the ureteroscope to those locations, you're not able to grab the stone with a conventional basket. So what we have is a steerable sheath that deploys a basket and can be controlled on the back end with a handle. So here's an example of a traditional basket. You can see there is a stone on the right. It's behind this occlusion, and we can't get around to it, so we're just trying desperately to get at that stone, and it's just not working. You kind of have to use the walls of the kidney to push the basket where you want it to go, which is not great. So this just goes on for a while, and they aren't able to reach the stone. And here's our device, an early prototype of this device, where we just have, again, our flexible shaft, high torque flexible transmission with our steerable tip. And since it's only 1 degree of freedom, well, really 2 or 3. I mean, insertion is 1 degree of freedom, bending is 1 degree of freedom, and then the rotation of the bending plane is 1. But all of that gets encoded into just manual controls on the handle. This is a fairly simple device. It's not robotic. It's just manually controlled. And you can see the steerable basket here at the end. And we're doing, in this video on the right, stone removal in a phantom kidney model. This is at scale. So just for context, the scope in question here is 3 millimeters in diameter, and then the steerable basket sheath is about 1 millimeter in diameter. So grab the stone, able to reach around the corner and grab the stone, pull it out. So I'm very happy to report that we have had, at this point, several successful human trials. And Bio reports the device is working well, and they're able to get stones out that they can't get with the normal tools. It's very satisfying to be able to reach around that corner. Okay, so that, I think we can stop there. There's a lot of other modeling slides we could do, but in the interest of time and questions, we can go back to questions. Thank you.
Any questions?
Yes?
For you, nice presentation, thank you. For the work you were doing with the stiffness modeling at the tip, how are you searching, like how much to, like where all to palpate? Are you
Oh, yeah.
using a raster pattern right now? Or?
Right now it's a grid-based search, but we're progressing to a sort of an information theoretic where to push next question. So working with Alan Kuntz on that problem, and he's got a great framework to try to do that. So we're about to do that. Yeah. It's good.
Because we were struggling with something similar, and I think everyone just uses Gaussian process regression to fill that void. And I was curious if you had a different approach to like densify the sparse points that you searched.
Yeah, that's a great question. I don't think I can speak to the details of it right now, but I'd love to chat more about what you're thinking about. Yeah.
Yeah, you showed an interesting example where you put like a lateral force and it effectively swayed.
Mm-hmm.
And I was thinking, well, yeah, that better be in tension, not in compression, as I remember. But have you thought about having crisscross?
Yes.
So there always will be a member in tension.
Yes. Well, the diagonal one can handle. They can all handle both tension or compression because they're.
Up to a point. Right?
Oh, you mean like for buckling? Yeah. Yes, that is a good point. We're not really thinking about buckling there, but yeah. So crisscrossing them. The trouble with crisscrossing them is they actually need to be able to independently slide with respect to each other. So they can't just be a cross in a monolithic structure because that just creates a rigid piece. So it would need to be, a member that passes through some holes and then another one, which starts to look like, a structure with some constraints on it that are very specific. But yeah, that's like kind of the next thing we're looking at is can we do a 3DOF version of that this in 3D where we've got like some crisscrossing rods that are just passively anchored at different points. Yeah. Very good. I didn't show this, but we did try in an earlier work. We tried to rigidify all of the degrees of freedom at the end effector by having 3D truss and then by having essentially 6 rods that would constrain all 6 degrees of freedom of the end effector, and that worked well. But we were using like everything in that system was an actuation rod, and it wasn't easy to. They're coming in at different angles, and so like mapping that back to the actuators was difficult. So this was sort of a simplification of the idea that's more practical for a conventional actuator system to do. Yeah, but I can pull up slides for that if you want in a minute. Other questions? Yes.
Very interested in your work on lithotripsy application. Can you use
use this concentric tube idea to construct the scope rather than just this basket device?
Yes.
The working channel of the scope.
Yes.
What would be the challenge
Yeah. Sorry, what was the last question?
What would be the challenge to construct a scope with this design?
I can't. It's not a particular challenge. It's just the fact that there's more that goes into a scope with imaging and jackets and things like that. So it's not just a two-tube nitinol construct, but right, it's all standard. Yeah. So to answer your question, yes, and we are doing a version of this called the Theoscope that's meant to be a very small imaging device for a variety of applications. Yeah.
One thing I see is can you inject irrigation fluid into such a device?
Yes.
The structure you show may have some gaps.
Yes. I don't have the most updated video, but we have an irrigation system with the basket and can because the basket sheath is smaller than the instrument channel, we can still do significant irrigation around the sheath itself in a conventional ureteroscope. Yeah, so the capability is there to do the irrigation. We could pull up some additional videos on the EndoTheia website that show that, as well as the full scope version of the technology. Yeah.
Thanks.
Yeah. Thank you. Yes.
About the model-based control slide that you showed, I'm curious that how you linearize your model, because I think that for input and output feedback linearization, the model, this method highly dependent and sensitive to the model parameters. So if from different environment it would be nonlinear, and how did you deal with the actuation saturation? And have you ever tried to linearize the Casserad model with like an LTI system, and then would be able to apply all types of controller on that one, because it's a highly nonlinear system and it's not fully controllable, I think, and observability and if I think even it's a very challenging task for these controllers. I have tons of questions.
Yeah. Yeah, I should have put the reference to the paper on that slide, but all of the things that you're raising are things that we did encounter, and there were challenges that we needed to overcome. So let me get back to it here. Yeah, it's this one, right? This one.
Yes, because it's...
Yeah. So to clarify, there's a robust outer loop controller that's doing sliding mode. That will account for parametric uncertainty. So that's that block on the left. I packed a lot of things into this one slide that's not fully explained. But so we're doing sliding mode control on the outer loop of the feedback linearization. And the input-output feedback linearization is just controlling essentially the acceleration of the tip. So with appropriate number of actuators, you can directly influence the acceleration at the tip in a one-to-one fashion through this input-output linearization. It is a feedback linearization. It's not a and so, but that linearization controller needs the full dynamic state of the robot, which is being given by an observer that is running a copy of the dynamic model. With forces injected to that model where we have sensors in order to push the model locations to the sensor locations. And so the idea is the rest of the robot dynamics will follow the data, follow the true state of the robot if those points are constrained to follow. So it's kind of a physically motivated observer, and then you can do the input-output feedback linearization, and you can put a robust controller around it. And so we were able to see, like, these simulations, I think, have a fair amount of parametric uncertainty in them between the model controller and the actual system. that said, like the practicalities that you mentioned, like actuator saturation, time delay of sensors and actuators, that did cause difficulty in actually getting this to work on physical system. This is a simulation. It does work in simulation with parametric uncertainty, but we have not yet seen it work fully in a real experiment with a physical robot. We have the pieces working, so we have the observer works well. It tracks the full state of the robot, even given just sparse measurements. And obviously the controller works in simulation. At some point, the limitations of hardware, I think, were getting to us, and yeah, so it's hard, as you rightly observe, and yeah, we're not there yet. This is not the best way to control a continuum robot. We're just trying to explore like what's possible. Can these highly underactuated models be treated this way from a controls perspective? Can we even theoretically formulate these kinds of controllers? That's what we were trying to
Can I
ask. Yeah.
What was the accuracy of the controller for reaching the target position?
In this paper, I don't remember, but it was highly accurate for the trajectory we were trying to follow. But it was a simulation, so their simulations are doomed to succeed. And yeah, even if it's a simulation with parametric error in it. Yeah.
Thank you.
Yeah. Thank you for your question. Yeah.
For your concentric push-pull
Yeah.
system, when you're bending the inner robot, does it affect the curvature of the outer robot as well, or are they like decoupled from that?
Yes, they are decoupled. It does not affect it. And this was a point of confusion for a long time. Like, why does it not? We're used to seeing like when you actuate a distal segment, it's going to exert a moment on the proximal segment, and it's going to try to push it, and you're going to have to resist that with the proximal segment actuation. That does not happen with these structures. There's something going on in the transition from asymmetric pattern to symmetric pattern, where those moments get canceled out. And if you cut a section right here, the push-pull forces are aligned, and so there's no internal moment there that needs to be resisted by bending. So it really does decouple it, which is, I think, unique to this design as opposed to tendon actuated or something else. Yeah.
Thank you.
Mm-hmm. Thank you. Yes.
I guess in a similar vein, and again, thank you very much for the talk. You mentioned briefly one of the projects on trying to decouple the axial and the torsional stiffness.
Mm-hmm. I kind of sped through that in the interest of time.
Just to make sure I understand the motivation correctly. So you want to maintain axial rigidity for those maybe like long transmissions through endoscopes.
Right.
But then for the torsional stiffness, what's the kind of benefit of having?
Oh yeah, well the way we change the bending plane is we turn the rotation of the tubes at the base. So if you want to resist, if it's curved this way and you want to resist an out of plane load, that's a torsional load on the transmission. So exerting forces on the end effector causes torsional loads, and generally, you just want faithful transmission. If I rotate 30 degrees on the back end through 7 feet of colonoscope, do I really get 30 degrees on the front end? So there's a lot of things with these transmissions where sometimes, if they accidentally get plastically deformed, then they'll have preferred ways that they will want to sit in the scope, and it'll be difficult to control them. So torsional authority, torsional control is a big part of this, and that's why we need them to be torsionally rigid. Yeah. But you mentioned the decoupling. If you just take a tube and you cut it, the percentage that you reduce the bending stiffness is almost always exactly the same as the percentage you will reduce the axial stiffness. So that's like a very baked-in trade-off to laser cutting tubes, unless you do something more creative and exotic. And we were trying to open that up. So like if you just take a brickwork pattern, the star is percentage of uncut. And you can see this, like, it's just a line of slope 1. That's the entire design space for an ordinary brickwork pattern. So there's no getting away from that unless you do something weird, like we did. So we were able to do it, to open it up a bit and get higher AE for a given EI. And we have some ongoing work that's trying to do even better than that. Yeah. This is a common problem in medical shaft design, because a lot of times, I mean, with a catheter or something, I mean, everybody wants these properties. If you have a shaft in a medical application, you probably want it to be really flexible in bending. You probably want it to be really stiff in torsion, and you probably want it to be pretty stiff in axial. And we really care about the axial because that's what's driving the actual manipulator. So, yeah. Great questions, guys.
So we got one more minute if there's any last questions.
Yes.
For the brickwork design, I'm trying to wrap my head around it. Does it allow the tube to bend in one bending plane?
No, it's omnidirectional. It's a uniform pattern around the circumference.
It's kind of like those shaft couples that have the.
Yes, it is. Yeah. Although, I mean, for a given brickwork design, like, it depends on the design. So if you have like alternating 90-degree cuts in pairs, that technically is omnidirectional. But when we made those and observed, they have preferred snapped locations. And so spreading the angles out in a more distributed pattern helps that. We found that you needed to go to like 45 degrees or more to kind of really get true continuous omnidirectional bending. There's some interesting results we had with the golden ratio about that. A slide that I cut, but we can look at it. Yeah.
Thank you.
All right. Please thank our speaker one more time. And thank you all for coming.